All right, momentum free response questions, the second set, number 5. Actually, there is very little momentum in this question until the very, very end is where it shows up. But that's okay. That's one of the reasons I put so many momentum questions in here, because they're a good review. So we have, zooming in a little bit here. So we have person, center of mass is right here, and they're going to swing on this swing through a lowest point, another point, and then this point, the key here is that this point is at the same height as their starting position. D and A are supposed to be at the same height at that point. So starting from rest, a 50 kilogram person swings along a circular arc from a rope attached to a tree branch over a lake, as shown in the figure above. Point D is at the same height as point A. The distance from the point of attachment to the center of mass of the person is 6.4 meters. Ignore air resistance and the mass and elasticity of the rope. Okay, thank you. All right. Person swings 2 times, each time letting go of the rope at a different point. On the first swing, the person lets go of the rope when first arriving at point C. Draw a solid line to represent the trajectory of the center of mass of the person when he releases the rope. All right. So the question is, when he lets go of the rope, is he moving? And your answer would be yes. He's still moving, and he's got a tangential velocity that would be like this. But he doesn't continue going like that forever, right? Gravity's involved. So he is basically a projectile launched at an angle like this, and he would fly like this in some sort of parabolic arc. But it would come out and down like that. He would have a tangential velocity that would start him off, and he'd immediately then fall back down like that. Cool? Makes sense. He's moving. Got it. No big deal. The next one is the tricky one, in my mind. A second time, the person lets go of the rope at point D. Draw a dashed line to represent the trajectory of the center of mass of the person when he releases the rope. This is actually an interesting question. They do a couple things. First of all, they continue drawing this arc. And that's kind of misleading, because homie isn't going past this point. How do I know that he is not going past this point? Well, he has so much potential energy to work with, say, from above the surface of the lake, right? So when he gets back to that same height, he stopped. Any kinetic energy he had down here has been turned back into potential. He ain't going up here. Nobody pushes him. So this is it, right here to here. So when he gets to this point, he is stopped. If he releases at that point, he is just a stationary object. It is as if he's just being dropped. What would he do? Trajectory is a bit of an unfair question too. He just falls. So that's a tricky question. It's a good question, because it forces you to realize, oh wait, all the kinetic energy is going to go back into potential. He's just, at that point, he's just going to drop. If he lets go down in here, he's going to do one of these. Okay. So that's a dash line. Okay, so that's tricky little questions, but good ones. And I put the same description here, but then we go to B. The center mass of the person standing on the platform at point A is 0.41 meters above the surface of the water. Calculate the gravitational potential energy when the person is at point A relative to when he's at the water. Okay, so straightforward. We're just doing MGH. He's a 50 kilogram person, so it's 50 kilograms. This is kind of a gimme question. Times a height of, G, 9.8. Times an initial height of, they gave us 4.1 above the water. And that's going to be our 0 mark, is the water. All right, so 50 times 9.8 times 4.1, 2009. So he has 2009 joules of energy at this point. C, the center of mass of the person at point B, the lowest point in the arc, is 2.4 meters above the surface of the water. Calculate the speed of the person's speed at that point. All right, conservation of mechanical energy here. All right, his mechanical energy here, since there's no friction or anything else like that, has to equal his mechanical energy here. At the start, his mechanical energy is all in potential. But down here, he's got some potential and some kinetic. So we would say the mechanical energy initially, when he's all the way up here, has to equal the mechanical energy when he's, say, at the bottom. At the top, it's 2009. We figured that out. It's potential energy. At the bottom, it is the potential energy he still has plus the kinetic energy he has at that point. Well, they give us enough information to find the potential energy, because they tell us he's 2.4 meters above. So it's 50 times 9.8 times 2.4 plus his kinetic energy, which is going to be 1/2 times 50 times this velocity that we're looking for at point B squared. There we go. So we got to work this guy out and solve for the velocity of B. So we're going to do 2009. Let's get this first. So 50 times 9.8 times 2.4 meters. It's 1,176 joules equals 2009 joules plus 25 times V, velocity of B squared. So subtract that from both sides. So 2009 minus 1176 divided by 25. Do you mind if I take the square root too? Let's go crazy. Take the square root to get rid of that. And I get a velocity of 5.77 meters per second when he's at point B. But it's a conservation of energy problem, mechanical energy. All right, so I get that as velocity of B, 5.77 meters per second. Suppose the person swings from the rope a third time, letting go of the rope at point B. Calculate R, the horizontal distance moved from where the person releases the rope at B to where he hits the water. Okay, so this is once again, a kinematics problem, which we're going to have to do up here somewhere. But at point B, which direction is his tangential velocity? Well, the good news is it's perfectly horizontal. So we have a horizontal projection. If you've done the last problem, or there's a few of them in here, they show up a lot. We'll figure out the time it takes in the y first. So the y dimension, he's got an initial height, 2.4. He's got an initial y velocity, which they made us find, no he doesn't, 0. Careful, this is the x velocity. It's launched horizontally. Almost got in trouble. Acceleration is negative 9.8. His final position is 0 when he hits the water. His final velocity, I don't know. But time is what I really think I want. And so, like earlier problems we've looked at, it's going to be y final equals 1/2 gt squared plus voy times t plus the initial position, initial height. But this goes to 0, and this comes over, so I have negative 2.4 meters equals negative 4.9 t squared. This is negative 4.9. Once again, it's just half of g. So it's just this boiled down to a number. This is gone. I just brought this over. This was 0. I'm going to do a quick division and a square root. So 2.4 divided by 4.9. That gets me 0.489795 blah 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 equals t squared. I need t, so I'm going to take the square root. So I get about 0.7 seconds. So he's in the air for 0.7 seconds. So now we go to the x dimension. But the good news, the x dimension does not have much going on. The change in x, which is really the distance he's going to land away from his release point. It's whatever this distance is here. He's going to go like this, boom. It's that distance right there. We'll just call that delta x. We don't know that, but we do know the original x velocity. That is the 5.77 meters per second. I do know the time now. That's why I went in the y dimension to get that. It takes some 0.7 seconds to make the trip. So rate times time equals distance. So that delta x is equal to 5.77 times 0.7. I get about just call it 4.04. So delta x is about 4.04 meters, and that's good for that. Now, we finally get to the momentum part of this. Oi, if the person does not let go of the rope, how does the magnitude of the person's momentum, PC, compare with the magnitude of the person's momentum at B? Well, this is the easiest part of the whole problem. I mean, he's the same mass the whole time, right? So basically, it's where is he going the fastest? Well, he's got to be going the fastest at B, right? Because as he goes back up this way, he's going to slow down because he's going to turn more of his energy, kinetic energy, into potential. So his momentum here at B has to be the larger than C. So which way is that? So is PC larger than B? No. PC is, I would go with that guy. And I would simply say momentum is mass times velocity, and his mass isn't changing, and his velocity is going to decrease because his kinetic energy is going to be turned into potential energy as he goes up there. Something like that. That should work, but pretty straightforward. So the momentum part of this was really not difficult at all.